Could our universe be one single black hole? This intriguing question has puzzled scientists and philosophers for thousands of years. And with new modern technology, scientists may have figured it out. Join us as we venture into this exploration and look for answers to some of the most profound questions we have about the universe and our existence. At the heart of some of the most dramatic cosmic phenomena lies an entity so mysterious and compelling that it has captured the imagination of scientists and the public alike: the black hole. Imagine the universe as a vast tapestry of galaxies, stars, and planets, all bound by the fundamental forces of nature. Within this cosmic dance, black holes are areas where gravity's pull is so intense that nothing, not even light, can escape once it crosses a certain boundary known as the event horizon. This makes them invisible to us and yet detectable through the effects they have on their surroundings. The concept of a black hole is not just a product of modern science. It stems from a combination of observations and the laws of physics as we understand them. According to Einstein's theory of general relativity, massive objects can warp the fabric of spacetime itself. When a star many times the mass of our Sun exhausts its nuclear fuel, it can collapse under its own gravity to a point where it creates a singularity, an infinitesimally small point in space where density and gravity become infinite. Surrounding this singularity, the event horizon marks the point of no return. It's not a physical surface, but a spherical boundary. Once crossed, all paths, even those at the speed of light, lead only inward, making escape impossible. This gravitational pull affects not just matter, but the path of light itself, leading to fascinating phenomena such as gravitational lensing, where light from stars behind a black hole is bent around it, creating rings of light or even multiple images of the same star. This effect has been observed and serves as a powerful tool for astronomers to detect and study these enigmatic objects. Black holes are not all of the same size. They can range from small stellar mass black holes, which are a few times the mass of our Sun, to supermassive black holes that reside at the centers of galaxies, including our own Milky Way. These giants can have masses millions to billions of times that of the Sun and play crucial roles in the evolution of galaxies. Their immense gravitational pull can influence the orbits of stars in the galaxy, and as they accrete matter, they can emit intense radiation that can be detected across vast distances. The study of black holes is not just an exercise in understanding the cosmos. It challenges and enriches our understanding of the fundamental laws of physics. They are natural laboratories for extreme physics, places where the gravitational force is so strong that it tests our theories of how the universe works on the most fundamental level. The recent observation of gravitational waves, ripples in the fabric of space-time generated by the collision of black holes, has opened a new window onto this dark and hidden side of the universe, offering insights into the nature of gravity, the behavior of matter and energy under extreme conditions, and the very structure of space-time itself. Now let's dive a bit deeper into how these structures are formed. The most common pathway to the formation of a black hole begins at the end of a massive star's life, a star significantly larger than our own Sun. Over millions of years, these colossal stars burn through their nuclear fuel, a process that balances the immense gravitational forces trying to compress them. However, this equilibrium cannot last forever. Once the nuclear fuel is exhausted, the star can no longer sustain itself against its own gravity. This leads to a dramatic finale. The star collapses. For stars with masses up to 3 times that of the Sun, this collapse results in dense remnants known as neutron stars. But for those with much greater mass, the story takes a more dramatic turn. The core collapses to such a degree that it forms a singularity, a point in space where density and gravity reach infinity, according to our current understanding of physics. This singularity is the heart of the black hole, surrounded by the event horizon, the point beyond which not even light can escape. This process is not merely theoretical. Astronomers observe the cosmos for signs of such cataclysmic events, using sophisticated telescopes that can detect the radiation emitted as a star dies and a black hole is born. These observations not only confirm the existence of black holes, but also provide insights into the properties of these fascinating objects. Yet, stellar collapse is not the only way black holes can form. Theoretical physics suggests other possibilities, such as the direct collapse of a gas cloud under certain conditions, bypassing the star phase entirely, or the mergers of neutron stars that produce gravitational waves detected by instruments like LIGO and Virgo, providing a new way to observe the universe. The scale of black holes can vary widely. Stellar black holes, formed from the collapse of individual stars, are just one category. There are also supermassive black holes, which reside at the centers of galaxies, including our own Milky Way, and are millions to billions of times more massive than our Sun. The origin of these supermassive black holes is still a subject of research and debate among scientists. Some theories suggest they formed from the collapse of massive gas clouds in the early universe, while others propose they grew from smaller black holes merging and accreting matter over billions of years. At their core, black holes are defined by three primary attributes: mass, spin, and charge. The mass of a black hole is a measure of its gravitational pull. Just like the Sun's gravity governs the orbits of the planets, the mass of a black hole dictates the gravitational force exerted on objects around it. However, the gravity of a black hole is so strong that beyond a certain point, known as the event horizon, not even light can escape, rendering the black hole invisible and marking the boundary between the known universe and a place where the rules of physics as we understand them cease to apply. The spin of a black hole, another of its defining characteristics, refers to its rotation. Black holes can spin at nearly the speed of light, influencing the space around them. This rotation twists the space-time fabric, a phenomenon predicted by Einstein's general relativity, and has profound effects on the behavior of matter near the black hole. The spin affects how a black hole interacts with its environment, including the way it pulls in matter and the jet emissions observed extending from some black holes. Charge, the least understood and most elusive characteristic, refers to the electric charge of a black hole. In theory, black holes can possess positive, negative, or no charge at all. However, most black holes observed are thought to have little to no charge because they quickly neutralize by attracting opposite charged particles from their surroundings. Beyond these fundamental characteristics, black holes exhibit behavior that challenges our understanding of physics. For instance, the singularity at a black hole's center represents a point where, theoretically, density and gravity become infinite, and the laws of physics as we know them break down. The event horizon, the boundary beyond which light cannot escape, signifies the point at which the black hole's gravitational pull becomes irresistible. This boundary is not a physical surface, but a region in space, marking the point of no return for matter and light alike. The study of black holes also reveals how they interact with their surroundings. As matter falls into a black hole, it heats up and emits X-rays, a process that allows astronomers to detect and study black holes despite their inherent invisibility. Furthermore, the gravitational influence of black holes on nearby stars and gas clouds provides clues about their presence and properties, allowing scientists to map their locations and estimate their masses. The question of whether anything can escape a black hole touches on the very edges of our understanding of the cosmos. Traditionally, black holes have been described as cosmic traps from which not even light, the fastest thing in the universe, can escape once it crosses the event horizon. This boundary marks the point of no return and is a key feature in the characterization of black holes. However, the story doesn't end there, thanks to the pioneering work of physicists like Stephen Hawking. Hawking introduced a fascinating concept known as Hawking radiation, a theoretical prediction suggesting that black holes are not entirely black, but can emit tiny amounts of thermal radiation due to quantum effects near the event horizon. This radiation implies that black holes can lose mass over time, slowly evaporating away to nothing. The process is exceedingly slow for black holes of stellar mass or larger, taking far longer than the current age of the universe to have any noticeable effect. For a black hole the mass of the Sun, the time it would take to evaporate completely is many orders of magnitude longer than the age of the universe. The existence of Hawking radiation bridges the realms of quantum mechanics and general relativity. two pillars of modern physics that are notoriously difficult to reconcile. It suggests that under certain conditions, particles can escape the grasp of a black hole, albeit in a form vastly different from what originally fell in. This quantum effect, while not allowing for escape in the traditional sense, no spaceship or signal crossing the event horizon could ever return to tell the tale, introduces a nuanced view of black holes as dynamic entities, not just insatiable voids. The implications of Hawking radiation extend beyond the mere possibility of escape from a black hole. They touch on fundamental questions about information loss and conservation in the universe. According to quantum theory, information, like the physical state of a particle, cannot be destroyed, but the apparent swallowing of information by black holes poses a paradox. Hawking radiation offers a potential resolution, suggesting that information could be encoded within this radiation, albeit in a form that would be almost impossible to decipher. The event horizon of a black hole represents a fascinating and critical boundary, a point of no return beyond which anything, matter or light, cannot escape the black hole's gravitational grip. This invisible threshold surrounds the singularity, where the black hole's mass is concentrated and defines the boundary between the observable universe and the mysterious interior of a black hole. To understand the event horizon, one can imagine it as the ultimate border, where the gravitational pull is so strong that the escape velocity exceeds the speed of light, approximately 299,792 kilometers per second. Since nothing can travel faster than light, crossing the event horizon means that there is no coming back. The size of the event horizon, known as the Schwarzschild radius, varies directly with the mass of the black hole. For a black hole with the mass of the Sun, this radius would be about 3 kilometers. However, black holes can have a wide range of masses, leading to significantly different event horizon sizes. A stellar mass black hole, formed from the collapsed core of a massive star, might have an event horizon just a few kilometers across, while a supermassive black hole, like the one at the center of the Milky Way galaxy, has an event horizon that spans millions of kilometers. The concept of the event horizon is not just a theoretical curiosity. It has practical implications for our understanding of the universe. The behavior of matter and energy near the event horizon provides insights into the laws of physics under extreme conditions. For instance, as matter spirals into a black hole, it accelerates and heats up, emitting X-rays and other forms of radiation that astronomers can detect and study. This phenomenon allows scientists to infer the presence of black holes and to estimate their mass and spin. Moreover, the study of event horizons challenges and enriches our understanding of space and time. According to general relativity, time itself slows down as one approaches the event horizon from the perspective of an outside observer. This leads to fascinating theoretical implications, such as the idea that, from the viewpoint of an observer falling into a black hole, they might reach the event horizon in a finite amount of time, while an outside observer would see them slow down and never actually witness them crossing the event horizon. Detecting black holes presents a unique challenge to astronomers. Despite their invisibility, scientists have developed ingenious methods to infer their presence and properties. One of the primary ways to detect a black hole is by observing the effects it has on its surroundings. When a black hole pulls in gas, dust, or other material from a star or interstellar space, this material accelerates and heats up, emitting X-rays and other forms of radiation that telescopes can detect. This radiation doesn't come directly from the black hole, but from the accretion disk, a swirling ring of matter that forms around it. The intense gravitational pull of the black hole affects the motion of nearby stars and gas clouds. Astronomers can observe these motions using telescopes equipped with sophisticated instruments, calculating the mass of the invisible object causing these effects. In some cases, the movement of stars orbiting an unseen mass can reveal the presence of a black hole, with their speeds indicating its mass. Another groundbreaking method involves gravitational waves, ripples in the fabric of spacetime caused by violent cosmic events, such as the collision of two black holes. Instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo have detected these waves, providing a new way to observe the universe and confirm the existence of black holes. These detections have not only confirmed the existence of binary black hole systems, but also provided information about their masses and the nature of their mergers. Additionally, the effect known as gravitational lensing, where a black hole bends light from objects behind it, can also indicate its presence. This phenomenon can magnify and distort the light from distant stars or galaxies, creating multiple images or rings of light known as Einstein rings. By studying these effects, astronomers can deduce the mass and position of the black hole causing the lensing. One of the most direct pieces of evidence for the existence of supermassive black holes comes from the Event Horizon Telescope, EHT, a global network of radio telescopes. The EHT captured the first ever image of a black hole's event horizon, or more accurately, the shadow it casts, surrounded by the glowing accretion disk. This historic achievement was made possible by combining data from radio observatories around the world to create a virtual Earth-sized telescope, capable of observing the black hole at the center of the galaxy M87, located about 55 million light-years away. This image provided visual confirmation of the presence of supermassive black holes and offered invaluable insights into their properties and the nature of gravity. Now, how small can black holes get? The smallest known black holes are those of stellar mass, which can range from about 5 times the mass of our Sun to several tens of solar masses. However, the discovery of what might be considered the smallest known black hole presents a more nuanced picture. This black hole, identified through observations of its gravitational effects on a companion star, has been estimated to have a mass of only about 3.3 times that of our Sun. This finding is on the lower end of what theories predict can form a black hole after a star exhausts its nuclear fuel and collapses under its own gravity. Such a small black hole provides crucial insights into the death of stars and the formation of compact objects in the universe. It exists at the boundary between neutron stars, dense remnants of collapsed stars not massive enough to form black holes, and black holes themselves, offering scientists a valuable opportunity to study the properties and behaviors of extreme states of matter and gravity. Determining the precise size or mass of this black hole involves observing the dynamics of the system it is part of, including the orbit of the companion star, and the X-rays emitted as material is pulled from the star and heated to extreme temperatures in the accretion disk around the black hole. These observations allow astronomers to infer the black hole's mass and consequently the size of its event horizon. The largest known black holes are found at the centers of galaxies, including our own Milky Way, and are classified as supermassive black holes. These gargantuan entities can have masses that are millions to billions of times greater than that of our Sun. The title for the largest known black hole often changes as new observations and discoveries are made, but one of the contenders is the black hole in the galaxy Abell 85, which hosts a black hole with a mass estimated at about 40 billion times the mass of the Sun. This black hole's event horizon, the boundary beyond which nothing can escape its gravitational pull, would span a distance so vast that it could encompass the orbits of all the planets in our solar system and beyond. Such supermassive black holes are not just points in space, but have profound effects on their surrounding environments, influencing the formation and evolution of galaxies. The immense gravitational pull of these black holes can draw in vast amounts of gas and dust, forming an accretion disk around the black hole where the material is heated to incredibly high temperatures, emitting copious amounts of radiation detectable across vast cosmic distances. The discovery and study of these supermassive black holes challenge our understanding of the universe, pushing the limits of physics as we know it. They serve as cosmic laboratories, allowing scientists to explore fundamental questions about the nature of gravity, the fabric of spacetime, and the ultimate fate of the universe. Let's talk a bit more about singularities. As we touched upon a bit earlier, a singularity is a point in space where the density of matter and the gravitational force are thought to become infinitely large. This means that within the singularity, the laws of physics as we know them no longer apply in the same way, leading to a realm of unknowns. When a massive star collapses under its own gravity at the end of its life cycle, if the mass is sufficient, it can lead to the formation of a black hole. The core of the star compresses into an infinitely small point, the singularity, where all the mass of the black hole is concentrated. This concentration of mass in such a tiny point creates a gravitational field so intense that not even light can escape, defining the black hole's event horizon. The singularity is a theoretical concept derived from general relativity, Albert Einstein's theory that describes gravity as the warping of spacetime by mass and energy. However, the existence of singularities pushes general relativity to its limits, indicating points where spacetime curvature becomes infinite. Scientists believe that to fully understand singularities, a theory of quantum gravity is needed, which would combine general relativity with quantum mechanics, the theory that governs the behavior of particles at the smallest scales. The behavior of time near a black hole is one of the most fascinating aspects of modern physics, revealing the profound effects of extreme gravity on the fabric of spacetime. According to Albert Einstein's theory of general relativity, gravity is the warping of spacetime by mass and energy. This warping affects not only the movement of objects in space, but also the flow of time itself. Near a black hole, where gravity reaches immense levels due to the concentration of mass in an incredibly small area, time behaves in ways that defy our everyday experience. As one approaches the event horizon of a black hole, the boundary beyond which nothing can escape, the gravitational pull becomes so strong that time begins to slow down relative to an observer far away from the black hole. This effect is known as gravitational time dilation. To an observer watching from a safe distance, objects moving closer to the event horizon appear to slow down, taking longer to complete actions such as falling into the black hole. In theory, as an object reaches the event horizon, it would appear to the distant observer to freeze in time, never quite crossing the event horizon. For someone or something actually falling into a black hole, the experience would be markedly different. According to general relativity, if you were to fall towards a black hole, you would notice your own clock to tick normally relative to your immediate surroundings. However, as you look outwards, the universe outside would appear to speed up due to the same gravitational time dilation effects. As you approach the event horizon, you would theoretically see the outside universe age rapidly. The closer you get to the singularity, the point of infinite density at the center of a black hole, the more extreme these effects become, leading to predictions that inside the event horizon, the concepts of space and time as we understand them may no longer apply in the same way. However, these predictions are based on our current understanding of physics, which combines general relativity for the macroscopic world with quantum mechanics for the microscopic world. The two theories do not yet fully align, especially under conditions of extreme gravity like those found near black holes. This discrepancy highlights one of the biggest mysteries in physics, the quest for a theory of quantum gravity that can describe the behavior of spacetime under the extreme conditions found near black holes. What are the different types of black holes? Black holes are not a one-size-fits-all phenomenon. They come in several types, each distinguished by its formation process and mass. These types range from the relatively small stellar mass black holes to the incomprehensibly large supermassive black holes found at the centers of galaxies. Additionally, there's a category that falls in between, known as intermediate mass black holes, and another theoretical type called primordial black holes, which are hypothesized to have formed shortly after the Big Bang. Stellar mass black holes are the most common type. They are typically formed from the remnants of a massive star that has ended its life cycle. Once such a star depletes its nuclear fuel, it undergoes a catastrophic collapse, leading to a supernova explosion. What remains can be a black hole if the remaining mass is about 5 to 20 times that of our Sun. These black holes are scattered throughout galaxies, often found in binary systems where they can accrete matter from a companion star. Intermediate mass black holes are more elusive and are thought to have masses ranging from 100 to several 100,000 times that of our Sun. They serve as a potential link between stellar mass and supermassive black holes, but their origins are less understood. Some theories suggest they could form through the merger of smaller black holes or from the collapse of massive clouds of gas in the early universe. Supermassive black holes, on the other hand, are behemoths with masses ranging from millions to billions of times that of the Sun. They reside at the centers of nearly all large galaxies, including our own Milky Way. The origins of supermassive black holes are still a matter of research and debate. One theory proposes they may have grown from smaller black holes that accumulated mass over billions of years, while another theory suggests they formed directly from large gas clouds collapsing under their own gravity in the early universe. Primordial black holes, while still theoretical, are thought to be the smallest type, potentially as small as a single atom, but with the mass of a large mountain. These are hypothesized to have formed in the high-density conditions shortly after the Big Bang, from fluctuations in the density of the universe at that time. Primordial black holes could have a wide range of masses, from a fraction of the Sun's mass to many times more. What is the role of quantum mechanics in understanding black holes? Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, plays a crucial role in deepening our understanding of black holes, entities traditionally described by the theory of general relativity. The intersection of these two fundamental theories presents a fascinating frontier in physics, particularly in how quantum mechanics influences our understanding of what happens at and near the event horizon of a black hole, as well as the fate of information that falls into a black hole. One of the key contributions of quantum mechanics to black hole physics is the concept of Hawking radiation, proposed by Stephen Hawking in the 1970s. According to this theory, black holes are not completely black, but emit radiation due to quantum effects near the event horizon. This radiation arises from pairs of virtual particles that constantly pop into and out of existence in empty space. Normally, these particle pairs annihilate each other almost immediately, but if one particle falls into the black hole while the other escapes, the latter can become real and be observed as radiation. Hawking radiation suggests that black holes can lose mass over time, leading to the possibility that they could eventually evaporate completely. This process bridges the gap between quantum mechanics and general relativity, providing a quantum mechanical explanation for a phenomenon occurring in a realm dominated by gravity. Another crucial aspect where quantum mechanics intersects with the study of black holes is the information paradox. This paradox stems from the question of what happens to the information about the physical state of objects that fall into a black hole. According to the principles of quantum mechanics, information cannot be destroyed, but the traditional understanding of black holes suggests that anything that crosses the event horizon is lost to the outside universe, raising the question of whether information is lost when it enters a black hole. Resolving this paradox requires a theory that integrates quantum mechanics with general relativity, pointing to the need for a theory of quantum gravity that can fully describe the behavior of space, time, and matter under the extreme conditions found near black holes. The role of quantum mechanics in understanding black holes is pivotal because it provides insights into the fundamental nature of reality, suggesting that the fabric of the universe at its most extreme is woven from both the curved spacetime of relativity and the probabilistic world of quantum mechanics. Researchers are actively exploring theories such as string theory and loop quantum gravity as potential frameworks that could unite these two pillars of modern physics, offering a more complete picture of how black holes operate and how they influence the structure of the universe. Through the lens of quantum mechanics, black holes are not just simple gravitational sinks, but complex entities that challenge our understanding of the fundamental principles of the universe, pushing scientists to rethink the nature of space, time, and matter. Now let's delve into a puzzling question. How could we theoretically survive entering a black hole? The notion of surviving a journey into a black hole is one that stretches the limits of our current understanding of physics, veering into the realm of theoretical speculation. Based on our current scientific knowledge, particularly the theories of general relativity and quantum mechanics, surviving a trip into a black hole appears to be highly improbable due to the extreme conditions encountered. However, for the sake of exploration and theoretical interest, scientists have pondered scenarios that could, in theory, allow for survival under certain conditions. One theoretical possibility involves a type of black hole known as a supermassive black hole. Supermassive black holes, found at the centers of galaxies, have such large event horizons and mass that the tidal forces at the event horizon, the differences in gravity's pull on different points, are less extreme than those of smaller stellar mass black holes. In theory, this could mean that an object or person could cross the event horizon of a supermassive black hole without being immediately torn apart by tidal forces. However, once inside, the person would not be able to escape due to the black hole's immense gravity, and the eventual approach toward the singularity would subject them to extreme tidal forces. Another theoretical concept that has been proposed is the idea of a Kerr black hole, a rotating black hole which, according to certain solutions of Einstein's equations, might contain regions known as Cauchy horizons within them. These regions could, theoretically, allow objects to enter without being destroyed instantly by gravitational forces. Some hypotheses suggest that these rotating black holes could have stable orbits within them, or even passages to other parts of the universe, or different universes altogether, often referred to as wormholes. However, these ideas remain purely speculative and are based on mathematical solutions that may not represent physical reality. Quantum effects are expected to play a significant role near these horizons, potentially destabilizing them and making survival or passage through them improbable. It's important to note that these scenarios are highly theoretical and rely on conditions and physics that are not well understood or proven to exist. The extreme gravitational gradients near and inside black holes, along with the unknown behavior of matter at these scales, make survival highly speculative. Moreover, the notion of information loss and the breakdown of known physical laws within a singularity add further layers of complexity to the question of survival. Let's talk about something a little different. What is the information paradox associated with black holes? The information paradox associated with black holes is a fascinating puzzle that sits at the crossroads of quantum mechanics and general relativity, challenging our understanding of the fundamental principles of the universe. This paradox arises from a conflict between these two pillars of modern physics over the fate of information that falls into a black hole. According to the principles of quantum mechanics, information, the physical state of all particles involved, is conserved. This means that it should be possible, at least in principle, to track the state of all particles and thus predict future states. However, when we consider black holes through the lens of general relativity, anything that crosses the event horizon is seemingly lost to the outside universe, including any information it carried. This leads to a stark contradiction. Quantum mechanics insists information cannot be destroyed, while the classical understanding of black holes suggests that information is irretrievably lost once it passes the event horizon. Stephen Hawking introduced the concept of Hawking radiation in the 1970s, showing that black holes could emit radiation due to quantum effects near their event horizons. While this radiation implies that black holes can eventually evaporate, Hawking initially suggested that the radiation would be entirely random and not carry any information about what fell into the black hole, further complicating the information paradox. The core of the information paradox lies in what happens to the information about the physical state of objects that fall into a black hole. If the black hole evaporates completely through Hawking radiation, and this radiation does not carry information about the material that fell in, then it seems that information is lost from the universe. This contradicts the quantum mechanical principle of information conservation, leading to the paradox. Physicists have proposed various solutions to resolve the information paradox, but none have been universally accepted. These include the idea that information might somehow be encoded in the Hawking radiation in a way that we do not yet understand, or that it could be preserved in a hypothetical Planck-scale remnant of the black hole, or even that it might be stored in a parallel universe or escape through a wormhole to another region of spacetime. How do black holes influence galaxy formation? Supermassive black holes, with masses millions to billions of times that of our Sun, exert a profound influence on their cosmic surroundings, despite the paradoxical nature of their visibility. Invisible in themselves, they are betrayed by the energetic phenomena surrounding them. The relationship between black holes and galaxies begins with the gravitational pull of the black hole, which can draw in gas and dust from the surrounding galaxy. As this material accretes around the black hole, it forms a hot, spinning disk known as an accretion disk. The friction and intense gravitational forces heat the disk to incredible temperatures, causing it to emit vast amounts of radiation, including visible light, X-rays, and other forms of electromagnetic radiation. This process can regulate star formation in the galaxy by heating and dispersing the gas that would otherwise cool and collapse to form new stars. Moreover, the energy and jets emitted by the accretion process around supermassive black holes can have a significant impact on their host galaxies. These jets can extend far beyond the galaxy's core, influencing the intergalactic medium and potentially limiting the amount of gas that falls into the galaxy, thereby affecting the galaxy's growth and the rate at which new stars are born. This self-regulating mechanism, where the black hole's activity can control the rate of star formation, suggests a symbiotic relationship between black holes and their host galaxies. Observations have shown a correlation between the mass of the supermassive black hole at the center of a galaxy and various properties of the galaxy itself, such as the bulge's mass and the velocity dispersion of the galaxy's stars. This correlation indicates that the growth of supermassive black holes is closely linked to the evolution of their host galaxies, although the details of this relationship are still a subject of ongoing research. Now let's think about an interesting idea. Could a black hole be a gateway to other universes? The idea that a black hole could serve as a gateway to other universes is a captivating concept that blends the boundaries between science, philosophy, and science fiction. While mainstream science and current observations do not support the existence of such gateways, the notion finds some theoretical footing in the realm of speculative physics and advanced cosmological theories. At the heart of this idea is the singularity, the point within a black hole where density and gravity are thought to become infinite. Some theoretical models suggest that the extreme conditions at the singularity could potentially warp spacetime in such a way that it creates a bridge or tunnel known as a wormhole. Wormholes, as hypothesized by Einstein and others through solutions to the equations of general relativity, could theoretically connect disparate points in spacetime, potentially allowing for travel between different universes or distant parts of our own universe. There are significant challenges and uncertainties associated with this idea. First and foremost, the extreme gravitational forces near and within a black hole would likely destroy any matter attempting to pass through, making the concept of travel through such a gateway highly speculative. Additionally, the stability of wormholes is a major issue. Theoretical models that allow for their existence often require forms of matter or energy that are not known to exist, such as exotic matter with negative energy density, to keep the wormhole open. The concept of other universes itself remains a topic of theoretical exploration, with ideas such as the multiverse existing primarily in the realm of theoretical physics rather than empirical observation. These theories propose that our universe might be just one of many, each with its own laws of physics and constants, but direct evidence for such universes remains elusive. Transitioning from possible gateways to other universes, we delve into another equally captivating and speculative idea, the multiverse theory. This theory suggests that our universe, with its vast expanse of billions of galaxies and seemingly infinite space, might just be one of an enormous number of universes that together comprise the multiverse. Each universe within this multiverse could potentially have its own distinct laws of physics, constants, and cosmic structures, varying dramatically or only slightly from our own. The multiverse theory emerges from various domains of theoretical physics, including interpretations of quantum mechanics, inflationary cosmology, and string theory. In one interpretation of quantum mechanics, for instance, the universe splits into multiple parallel versions of itself with every quantum decision, leading to a near-infinite branching of realities. This interpretation suggests that there could be countless universes where different versions of events and existences play out. Inflationary cosmology provides another foundation for the multiverse theory. It posits that the rapid expansion of space after the Big Bang could have led to the creation of multiple disconnected regions of spacetime, each evolving into separate universes. These universes could be infinitely numerous, with some potentially having physical laws and constants vastly different from our own. String theory, a framework in theoretical physics that attempts to reconcile quantum mechanics and general relativity, also lends credence to the idea of the multiverse. Moreover, while the mathematics of general relativity allows for the existence of wormholes, there is no empirical evidence to support their existence. The conditions near a black hole's singularity, where quantum effects are expected to dominate, are not well understood. The merging of quantum mechanics with general relativity, necessary to fully grasp the physics of singularities and the potential for wormholes, remains one of the greatest challenges in theoretical physics. Diving deeper into the mysteries of space, we encounter an interesting question. Could our universe itself be nestled within the confines of a black hole? This intriguing idea ties together the concepts of black holes, wormholes, and the very structure of the universe in an imaginative exploration of the boundaries of cosmology and theoretical physics. The hypothesis that our universe could reside inside a black hole stems from the similarities in the theoretical properties of black holes and the universe's observed characteristics. Both are governed by the laws of general relativity, which describes how mass and energy influence the curvature of spacetime. A black hole is a region of spacetime where gravity is so strong that nothing, not even light, can escape. This definition intriguingly mirrors the initial conditions of our universe, which began from a singular point of infinite density and temperature, expanding outward in the Big Bang. One aspect of this speculation involves considering the nature of singularities, points of infinite density at the center of black holes, according to classical general relativity. If our universe originated from such a singularity, could it be that it is situated within a black hole existing in a larger universe? This scenario would imply that each black hole could potentially give birth to a new, separate universe within it, contributing to a fractal-like multiverse where universes beget universes. However, this hypothesis faces significant scientific challenges and remains highly speculative. The conditions at a singularity, where densities and gravitational forces become infinite, are not well understood and represent a point where classical physics breaks down. Quantum effects, which are crucial at such scales, are not accounted for in general relativity, indicating a need for a theory of quantum gravity to better understand these extreme environments. The observable universe appears to be flat, homogeneous, and isotropic on large scales, with a very specific distribution of matter and energy. The mechanics of how such a structure could form inside a black hole, and how we could observe the universe as we do from such a vantage point, remain unexplained within current theoretical frameworks. Is there any evidence that supports us living inside a black hole? While the concept is largely hypothetical and not supported by direct empirical evidence, it arises from intriguing aspects of theoretical physics and cosmology that invite us to ponder the nature of the universe and the mysteries it holds. Firstly, the concept of a universe within a black hole is supported more by theoretical extrapolation than by concrete evidence. It builds on the understanding that the conditions at the singularity of a black hole, where density and gravitational forces are thought to be infinite, mirror the believed conditions of our universe at the moment of the Big Bang. Both scenarios involve extreme density and the potential for rapid expansion, suggesting a parallel that has intrigued some theorists. Another point of theoretical support comes from attempts to unify general relativity, which governs the behavior of large-scale cosmic structures, with quantum mechanics, which explains the behavior of particles at the smallest scales. Some solutions to the equations of general relativity suggest that black holes could contain regions where the fabric of spacetime curves back on itself, potentially creating bridges to other universes or allowing for the birth of new universes within their confines. These solutions lead to speculation about the nature of singularities and whether they could be gateways rather than endpoints. Additionally, the observed uniformity and flatness of the universe, as well as the distribution of cosmic microwave background radiation, raise questions about the initial conditions of the universe that some theorists argue could be explained by a black hole-like scenario. However, These observations are also consistent with the widely accepted model of cosmic inflation, which does not require the universe to be inside a black hole to explain its observed properties. It's important to note that the idea of our universe residing inside a black hole remains a fringe concept within the scientific community. The evidence supporting this theory is indirect and speculative, relying on theoretical models that are yet to be empirically verified. The search for a theory of quantum gravity, which could explain the behavior of matter and spacetime under the extreme conditions of black holes and the Big Bang, is ongoing. Such a theory might provide more definitive answers to these profound questions. Now, how would living inside a black hole affect our perception of reality? Us living inside a black hole, if such a concept were physically plausible, would fundamentally challenge our understanding of reality as dictated by the laws of physics as we know them. Black holes, as predicted by general relativity, warp space-time to an extreme degree due to their immense gravity. If our universe resided within such a context, it could imply that the space-time fabric of our universe is shaped in ways that differ significantly from our current understanding. Firstly, the extreme gravitational forces characteristic of a black hole would, theoretically, have profound effects on time. Time dilation, a phenomenon where time moves slower in stronger gravitational fields, is a well-established consequence of relativity. If we were inside a black hole, this effect could mean that our perception of time might be vastly different from what we would experience in a less gravitationally intense environment. However, since we would have no external point of reference, this altered flow of time would be our normal, and we might not perceive it as unusual in any way. Secondly, the curvature of spacetime within a black hole could affect how we perceive the universe's structure and dimensions. In the extreme curvature near a black hole's singularity, the conventional dimensions of space could behave in ways that defy our usual understanding. This might lead to a reality where straight lines no longer appear straight, and distances become distorted. However, within the hypothetical scenario of our universe existing in such a state, these conditions would shape the very laws of physics and the structure of the cosmos that we observe. Our science, mathematics, and understanding of the universe would have developed within this framework, making these conditions our baseline for normal. Moreover, the concept of an event horizon within a black hole, a boundary beyond which information cannot escape, raises intriguing questions about the universe's observable limits. If our universe were inside a black hole, the event horizon could theoretically represent the boundary of the observable universe itself. This boundary could limit our ability to observe and understand the full extent of our universe, confining our perception of reality to what lies within. As we are on the topic, let's talk about this. How does the concept of space-time curvature relate to black holes? Space-time curvature is the idea that the presence of mass and energy can warp the four-dimensional fabric of the universe, comprising 3 spatial dimensions and 1 time dimension. This warping or curvature is what we perceive as gravity. Rather than viewing gravity as a force acting at a distance, general relativity describes it as the effect of this curvature on the motion of objects. The more massive an object, the more it warps the space-time around it. Black holes serve as the most extreme examples of space-time curvature. They are formed when a massive star collapses under its own gravity at the end of its life cycle, compressing its mass into an incredibly small point known as a singularity. This singularity represents a point of infinite density and, according to the equations of general relativity, an infinite curvature of space-time. Surrounding the singularity is the event horizon, the boundary beyond which the curvature of space-time is so steep that not even light can escape the gravitational pull, rendering the black hole invisible to the outside world. The concept of space-time curvature is essential in understanding how black holes interact with their surroundings. For instance, the extreme curvature near a black hole's event horizon affects the path of light and matter. Light rays passing close to a black hole can be bent, a phenomenon known as gravitational lensing, which allows astronomers to detect black holes indirectly by observing how they distort the light from stars and galaxies behind them. Moreover, the curvature of space-time around a black hole also has profound implications for the concept of time. Time dilation, a direct consequence of space-time curvature, means that time passes more slowly in stronger gravitational fields. Near a black hole's event horizon, this effect becomes so pronounced that, theoretically, time would appear to stand still to an observer at a distance. This relationship between space-time curvature and black holes not only underscores the predictive power of general relativity, but also highlights the ongoing challenges faced by physicists. The singularity at the heart of a black hole, where space-time curvature becomes infinite, represents a point where the laws of physics as we know them break down. This breakdown indicates the need for a theory of quantum gravity that can reconcile general relativity with the principles of quantum mechanics, offering a unified description of reality under the most extreme conditions. Moving away from space-time curvature around black holes, we venture into a related and equally compelling concept, the cosmic censorship hypothesis. This hypothesis is a cornerstone of theoretical physics that addresses the nature of singularities, those points of infinite density and gravity predicted by general relativity to exist at the centers of black holes. Proposed by Roger Penrose in 1969, the cosmic censorship hypothesis plays a pivotal role in our understanding of the universe's most mysterious phenomena. The essence of the cosmic censorship hypothesis is its proposition that the universe censors the existence of naked singularities, ensuring that such singularities cannot be observed from the outside universe. In more technical terms, the hypothesis suggests that every singularity, except possibly the one at the beginning of the universe, is hidden within an event horizon, the boundary of a black hole beyond which not even light can escape. This means that the extreme conditions and the breakdown of physical laws expected at singularities are not exposed to the external universe, preserving the predictive power of general relativity outside the event horizon. There are two main versions of the cosmic censorship hypothesis, the weak and the strong forms. The weak cosmic censorship hypothesis asserts that singularities produced by gravitational collapse are always hidden within black holes, thereby inaccessible to distant observers. This version allows for the theoretical possibility that an observer falling into a black hole might encounter a singularity, but this encounter would not affect the universe outside the event horizon. The strong cosmic censorship hypothesis goes further, suggesting that singularities are not just hidden from distant observers, but are also inherently unobservable because the laws of physics, as described by general relativity, continue to predict the universe's evolution without interruption. In essence, it implies that the universe is deterministic, and the behavior of physical systems can be predicted under all conditions, excluding the singularity that might have given birth to the universe itself. Now, how do black holes merge, and what does this tell us about our universe? Black holes merge when two of these incredibly dense objects come into close proximity and fall into a mutual orbit due to their gravitational attraction. Over time, as they emit gravitational waves, ripples in the fabric of space-time predicted by Einstein's general relativity, they lose energy. This loss of energy causes the black holes to spiral closer and closer until they eventually collide and merge into a single, larger black hole. The final stages of this spiral and merger happen very quickly in cosmic terms, releasing a tremendous amount of energy in the form of gravitational waves. The detection of these gravitational waves has opened a new window into understanding our universe. The first direct observation of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, was from the merger of two black holes, providing solid evidence of black holes' existence and the dynamic nature of space-time. These observations confirmed a key prediction of general relativity and marked the birth of gravitational wave astronomy. Black hole mergers tell us a great deal about our universe. First, they confirm that black holes can exist in pairs and groups, suggesting that they are common components of galaxies. Many galaxies, including our own Milky Way, are believed to have supermassive black holes at their centers. The discovery of merging black holes provides clues about the history of galaxies, including how they form and evolve over time. It is thought that when galaxies merge, a common event in the cosmic scale, their central black holes can eventually spiral together and merge, reshaping the galaxy's core and influencing its future development. Moreover, the study of gravitational waves from black hole mergers offers insights into the properties of black holes, such as their masses and spin rates, and the nature of gravity itself. By analyzing the waves' characteristics, scientists can test the predictions of general relativity under the most extreme conditions, further our understanding of fundamental physics, and explore the possibility of new physics beyond Einstein's theory. Gravitational waves also provide a new method for observing the universe. Unlike electromagnetic radiation, light, which can be absorbed or scattered, gravitational waves pass through matter almost unimpeded, offering a clear view of events that would otherwise be hidden, such as the merging of black holes. This new form of observation complements traditional telescopes, enabling astronomers to study cosmic events that are invisible in light, further unraveling the mysteries of the cosmos. Continuing our journey through the cosmos, we now bridge the gap between the elusive phenomena of gravitational waves and the equally mysterious concept of dark matter, particularly focusing on its interaction with black holes. Dark matter, an invisible form of matter that does not emit, absorb, or reflect light, comprises about 85% of the universe's total mass. Its presence is inferred from its gravitational effects on the motion of stars and galaxies, as well as on the bending of light, a phenomenon known as gravitational lensing. The interaction between dark matter and black holes is a topic of significant interest and ongoing research in astrophysics. While dark matter does not interact with electromagnetic radiation, making it invisible to traditional telescopes, it does exert gravitational forces and can therefore influence and be influenced by black holes. One of the key ways in which dark matter is thought to interact with black holes is through accretion. Just as black holes can draw in ordinary matter from their surroundings, they can also accrete dark matter. When dark matter particles come close enough to a black hole, they can be captured by its intense gravitational field and add to the black hole's mass. This process is particularly intriguing because it could potentially reveal more about the nature of dark matter, which remains one of the greatest mysteries in physics. The distribution of dark matter in galaxies and the larger cosmic structures could be influenced by the presence of supermassive black holes at the centers of galaxies. These black holes might act as sinks for dark matter, altering the distribution of dark matter in their vicinity. Additionally, the merger of black holes, as detected through gravitational waves, could provide insights into the distribution of dark matter in the universe by offering clues about the environments in which these mergers occur. Researchers also speculate that dark matter could play a role in the growth of black holes, especially in the early universe. If regions of high dark matter density existed in the early universe, they could have provided a fertile ground for the formation and rapid growth of black holes. This interaction between dark matter and black holes in the early cosmos could help explain the formation of supermassive black holes observed at the centers of galaxies, including our own Milky Way. Venturing from the theoretical interplay between dark matter and black holes, we explore the possibility of a civilization advancing technologically enough to manipulate black holes. This inquiry takes us to the fringes of astrophysics and speculative engineering, where the realms of current scientific understanding meet the expanses of future possibilities. Imagining a civilization that can manipulate black holes requires us to consider the leaps in energy consumption, control, and technological capabilities far beyond our current scope, potentially classifying such a civilization as Type 2 or 3 on the Kardashev scale. This scale is a theoretical framework that categorizes civilizations based on their energy harnessing capabilities, ranging from planetary to galactic scales. The manipulation of black holes suggests a myriad of purposes and methods, from energy extraction, akin to a cosmic-scale Dyson sphere capturing energy from a black hole's accretion disk, to the creation or stabilization of wormholes for faster-than-light travel or instantaneous communication across the cosmos. These concepts, while rooted in the equations of general relativity and quantum mechanics, also bring to the forefront the immense challenges and theoretical advancements required to turn such speculative ideas into reality. Energy extraction from black holes, for instance, would offer a civilization an almost unimaginable power source, given the immense energy released by matter as it accelerates and heats up before crossing the event horizon. Similarly, the manipulation of gravitational waves produced by the merger of black holes could open up novel methods of communication or propulsion, leveraging the fabric of spacetime itself. The notion of using black holes as gateways, through the theoretical possibility of wormholes, introduces the concept of bending spacetime to create shortcuts across the universe. This would not only revolutionize travel and communication, but also require an unprecedented understanding of spacetime, gravity, and quantum mechanics, far beyond our current knowledge. The unique conditions around black holes could be harnessed for advanced computational processes or data storage, exploiting the extreme gravitational forces and the peculiarities of quantum information theory. However, such feats would necessitate technologies capable of operating in environments of extreme energy and gravity without succumbing to the destructive forces present. Now, what are some of the ethical implications of exploring black holes? One ethical concern revolves around the responsibility we hold as a species in interacting with fundamental aspects of the universe. Black holes, as regions of spacetime with extraordinary gravitational effects, play crucial roles in the cosmic balance and the evolution of galaxies. Interfering with or attempting to manipulate these entities could have unforeseen consequences, not only on a local cosmic scale, but potentially on the stability of the universe itself. The precautionary principle suggests that in the absence of a comprehensive understanding of the consequences, caution should be exercised. The pursuit of technologies capable of exploring or manipulating black holes raises questions about the distribution of such powerful tools. Who would have access to these technologies, and how would their use be regulated? The potential for misuse or unintended consequences necessitates a global dialogue and international agreements to ensure that such advancements are pursued responsibly and for the benefit of all humanity, rather than becoming the domain of a privileged few. Another ethical dimension concerns the potential risks involved in exploring or interacting with black holes. Theoretical proposals such as sending probes into black holes or attempting to harvest energy from them come with significant unknowns. The safety of such missions, the risk of triggering unforeseen events, and the moral implications of potentially altering the natural course of cosmic phenomena warrant careful consideration. The value of scientific knowledge gained must be weighed against these risks. The mission to understand black holes and the broader universe challenges us to reflect on our place in the cosmos. It raises philosophical questions about the limits of human ambition, the nature of existence, and our responsibilities not only to our own planet and species, but to the universe as a whole. As we push the boundaries of exploration, we must consider the legacy we wish to create and the kind of cosmic citizens we aspire to be. What are the limits of our current technology in studying black holes? One of the primary limitations is the inherent nature of black holes themselves. Since no light can escape from within the event horizon, direct observation of a black hole is impossible with current technology. Scientists rely on indirect methods to study black holes, such as observing the effects of their immense gravity on nearby stars and gas. For instance, the detection of accretion disks, rings of gas and dust swirling around black holes, provides evidence of their presence. These methods, while powerful, offer only a glimpse into the complex behavior of black holes and their immediate surroundings. Another significant challenge is the resolution and sensitivity of our telescopes. While recent advancements, such as the Event Horizon Telescope, EHT, have allowed us to capture the shadow of a black hole against the backdrop of its accretion disk, these observations require global collaboration and the synchronization of radio telescopes across the Earth. The EHT's achievement in imaging the black hole in the galaxy M87 was a monumental step forward, yet it also underscored the limitations of our current observational capabilities. Imaging black holes in more detail or observing smaller or more distant black holes remains beyond our reach with current technology. Gravitational wave astronomy, a relatively new field made possible by facilities like LIGO, Laser Interferometer Gravitational Wave Observatory, has opened a new window into the study of black holes by detecting the ripples in spacetime produced by merging black holes. However, this technology also has its limits. Current gravitational wave detectors are most sensitive to specific mass ranges and merger frequencies. This means that certain black hole mergers, especially those involving very large or very small black holes, might go undetected. Enhancing the sensitivity and frequency range of gravitational wave observatories is a priority for future research. The vast distances to many black holes pose a significant challenge. Even with powerful telescopes, observing the details of black hole systems billions of light-years away requires overcoming immense technical hurdles. The faint signals from distant corners of the universe are often obscured or diluted by cosmic dust, gas, and other sources of interference. Lastly, our theoretical understanding of the physics of black holes, particularly at the intersection of general relativity and quantum mechanics, is incomplete. This theoretical gap limits our ability to devise experiments and observations that could fully unravel the mysteries of black holes. Advancements in theoretical physics, alongside technological innovations, are crucial for pushing the boundaries of black hole research. So, how would the study of black holes impact other fields of science? In physics, the study of black holes challenges our grasp of fundamental forces and particles. The extreme gravitational forces near black holes, where spacetime curvature reaches its peak, provide unique conditions to test Einstein's theory of general relativity against quantum mechanics. This ongoing dialogue between the two pillars of modern physics seeks to uncover a unified theory that can describe the behavior of the universe at all scales. Insights gained from black holes have propelled forward the search for quantum gravity, a theory that aims to meld the quantum and the cosmic into a single coherent framework. Additionally, black holes have a profound impact on the field of thermodynamics through the concept of Hawking radiation, which suggests that black holes emit radiation due to quantum effects near their event horizons. This phenomenon challenges traditional notions of entropy and information, leading to new understandings in the thermodynamics of black holes and sparking debates on the nature of information loss in the universe. These discussions extend into the realm of information theory, questioning how information is stored and transformed in the universe. The detection of gravitational waves from merging black holes has also influenced the field of astronomy, opening a new window into the universe. Gravitational wave astronomy allows scientists to observe cosmic events that are invisible in electromagnetic spectra, offering insights into the life cycles of stars, the formation of galaxies, and the early moments of the universe. This new method of observation has implications for cosmology, providing a novel way to measure the expansion rate of the universe and to test theories about its overall structure and evolution. Furthermore, the study of black holes touches on computational science, as simulating the complex dynamics of black holes and their interactions with the surrounding matter requires sophisticated algorithms and immense computational power. These efforts not only advance our understanding of black holes, but also drive innovations in computational techniques and technologies. In philosophy and theoretical science, black holes inspire questions about the nature of reality, time, and space. They challenge our conceptual frameworks and encourage a deeper examination of the principles that underlie our understanding of the universe. This philosophical inquiry informs scientific theory, guiding researchers in framing their questions and interpretations of data. It's important to address the misconceptions that often cloud public understanding of these cosmic enigmas. Despite their prominence in both scientific research and popular culture, black holes are frequently misunderstood, leading to a blend of myth and reality in the collective imagination. Addressing these misconceptions not only clarifies our understanding but also highlights the incredible nature of black holes as revealed by modern astrophysics. One prevalent misconception is the idea that black holes act as cosmic vacuum cleaners, endlessly devouring all matter in their vicinity. In reality, black holes exert gravitational forces similar to other objects of comparable mass. A black hole does not actively suck matter any more aggressively than a star of the same mass would. Matter falls into a black hole only if it comes extremely close to the event horizon, the point of no return. Otherwise, planets, stars, and gas clouds can orbit black holes safely without being drawn in, just as the Earth orbits the Sun. Another common misunderstanding is the belief that black holes are infinitely dense holes in the fabric of spacetime. While it's true that the density within a black hole's singularity, where all its mass is thought to be concentrated, is incredibly high, describing black holes as holes is misleading. They are better thought of as extremely dense objects with strong gravitational fields. The term hole stems from their inability to emit light, making them invisible against the backdrop of space, rather than implying an actual hole in space. There's also a misconception about the visibility of black holes. Many assume that black holes are completely invisible, but the regions around them can be among the brightest objects in the universe. As matter falls towards a black hole, it heats up and emits intense radiation before crossing the event horizon. This process can produce luminous accretion disks and powerful jets that are observable across vast distances, making black holes indirectly visible to astronomers. Some believe that nothing can escape a black hole, not even information. However, theoretical work, notably by Stephen Hawking, suggests that black holes emit radiation, Hawking radiation, due to quantum effects near the event horizon. This radiation allows black holes to lose mass over time, providing a theoretical mechanism for the escape of energy and, consequently, information, albeit in a highly transformed manner. This challenges the notion of black holes as eternal prisons for matter and energy. Lastly, the portrayal of black holes as portals to other universes or dimensions in science fiction has fueled misconceptions. While theories about wormholes and the structure of spacetime permit speculative discussions about connections to other parts of the universe or multiverse, current scientific understanding does not support the idea of using black holes as gateways for interstellar or interdimensional travel. These concepts remain firmly in the realm of theoretical physics, without empirical evidence to support their existence or practicality. Let's dive into a fascinating topic. How does the concept of a black hole universe influence science fiction? In science fiction, black holes are often portrayed as gateways or portals, a concept that, while lacking empirical support in scientific reality, provides a rich narrative device. The idea of traveling through a black hole to distant parts of the universe, or even to other dimensions or parallel universes, is a common trope. This concept taps into the human desire for exploration and the unknown, offering a cosmic shortcut to the far reaches of space and the tantalizing possibility of encountering alternate realities. The extreme conditions around black holes also serve as a backdrop for exploring the limits of human endurance and technology in science fiction. Stories might depict spacecraft attempting to navigate the perilous regions near a black hole, contending with intense gravitational forces, time dilation, and the threat of being pulled beyond the event horizon. These narratives often delve into the physical and psychological challenges faced by characters in these extreme environments, reflecting broader themes of resilience, survival, and the human spirit's tenacity. Black holes in science fiction are also used to explore philosophical and existential questions. The concept of time coming to a standstill at the event horizon, the mystery of what lies within a black hole, and the notion of information being lost or transformed all serve as metaphors for broader questions about the nature of existence, reality, and our place in the universe. Science fiction uses these themes to delve into questions of identity, the nature of consciousness, and the boundaries of scientific understanding. The depiction of black holes in science fiction often reflects current scientific understanding and speculation, albeit with creative liberties. As our scientific knowledge of black holes has evolved, so too have their portrayals in science fiction, shifting from fantastical ideas of cosmic whirlpools to more nuanced representations based on relativistic physics and quantum mechanics. This interplay between science and fiction enriches both fields, with science fiction often anticipating or inspiring scientific inquiry and discovery. Let us talk a bit about the future. What coming missions are planned to study black holes? One of the most anticipated missions is the Event Horizon Telescope, EHT, project's ongoing efforts. Building on its groundbreaking achievement of capturing the first image of a black hole's event horizon in the galaxy M87, the EHT collaboration plans to refine its techniques and expand its network of radio telescopes. The goal is to achieve higher resolution images of black holes and possibly capture dynamic processes occurring near the event horizon, such as matter falling into a black hole or jets of particles being ejected. Another significant mission is the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory planned by the European Space Agency, ESA, with a launch anticipated in the early 2030s. LISA aims to detect gravitational waves emitted by merging supermassive black holes in the centers of galaxies, as well as other cosmic events. By observing gravitational waves in a lower frequency band than Earth-based detectors like LIGO and Virgo, LISA will open a new window into the study of black hole mergers across a wider range of masses and distances. NASA's Athena Advanced Telescope for High-Energy Astrophysics, scheduled for launch in the early 2030s, is another mission aimed at unraveling the mysteries of black holes. Athena will be equipped with a large X-ray telescope designed to study the hot and energetic universe. It will observe large-scale structures and the dynamics of supermassive black holes, shedding light on how black holes grow and influence their host galaxies. The continued operation and future upgrades of existing space-based observatories, such as the Chandra X-ray Observatory and the Hubble Space Telescope, alongside ground-based telescopes, will play a crucial role in black hole research. These facilities will continue to provide valuable data on the behavior of matter near black holes, the properties of black hole jets, and the distribution of stellar mass black holes within our galaxy. Emerging technologies and theoretical developments may also pave the way for new types of missions that could directly probe the environments near black holes or employ novel methods of observation, such as using the effects of black holes on the cosmic microwave background radiation to study their properties. Exploring the origins of the universe naturally leads to intriguing questions about the Big Bang and its potential connections to black holes. The Big Bang theory, the prevailing cosmological model, describes the universe's birth as a singular explosion from an infinitely dense and hot state, expanding over time to form the cosmos as we know it today. This initial singularity shares conceptual similarities with the singularities at the centers of black holes, where density and gravity are also thought to be infinite. However, the comparison raises complex issues within our current understanding of physics. The singularity at the heart of a black hole, according to general relativity, is a point where gravitational forces compress matter to an infinitely small point with infinite density. This description aligns superficially with the Big Bang's initial state, suggesting a tempting analogy between the two. However, there are significant differences in the context and characteristics of these singularities that challenge a direct correlation. Firstly, the singularity in the Big Bang theory is not surrounded by an event horizon, the defining boundary of a black hole beyond which no information can escape. The universe's expansion from the Big Bang singularity was outward into what became spacetime itself, not confined within a pre-existing spatial fabric. In contrast, a black hole singularity exists within our universe's spacetime, influencing the surrounding space but not creating it. Secondly, the laws of physics as we know them, including general relativity, break down at singularities. While this is true for both the Big Bang and black hole singularities, the process of time and the evolution of the universe from the Big Bang singularity involves the expansion of spacetime and the cooling of the universe from an extremely hot, dense state, leading to the formation of matter, stars, galaxies, and the large-scale structure of the cosmos. This process is fundamentally different from the inward collapse and accretion associated with black hole formation. Furthermore, while some speculative theories suggest that our universe could be the interior of a black hole existing in a higher dimensional space, these ideas extend beyond the current empirical framework and into the realm of theoretical physics. They often involve concepts from string theory and other attempts at quantum gravity, aiming to reconcile the quantum and relativistic descriptions of singularities. However, these theories remain speculative without direct empirical support. Let's take a look at this question. Can black holes solve the mystery of the universe's missing mass? The mystery of the universe's missing mass, often referred to as the dark matter problem, is a central puzzle in modern astrophysics. Observations of the rotation rates of galaxies and the movements of galaxy clusters indicate that there is far more mass in the universe than can be accounted for by visible matter alone. This unseen mass exerts gravitational forces influencing the behavior of stars and galaxies, yet it does not emit light or interact with electromagnetic radiation in the way that ordinary matter does. The question of whether black holes can solve this mystery is intriguing, linking the enigmatic nature of black holes with the broader mysteries of the cosmos. Black holes, particularly the supermassive ones located at the centers of galaxies, contribute significantly to the mass of those galaxies. However, even when accounting for both stellar mass black holes, resulting from the collapse of massive stars, and supermassive black holes, the total mass they represent falls short of explaining the vast quantities of missing mass inferred from astronomical observations. The discrepancy leads scientists to conclude that black holes, while contributing to the mass of galaxies, are not the primary solution to the dark matter problem. The leading candidate for dark matter is a form of matter that does not interact with light or any other form of electromagnetic radiation, making it invisible and detectable only through its gravitational effects. This matter is hypothesized to be composed of particles that have not yet been discovered, possibly existing beyond the standard model of particle physics. Various theoretical particles have been proposed, including WIMPs, weakly interacting massive particles, and axions, but none have been directly detected as of yet. Efforts to understand dark matter include direct detection experiments, which aim to observe dark matter particles interacting with ordinary matter in highly sensitive detectors, and indirect detection methods, which seek to identify the byproducts of dark matter interactions or decays occurring in space. Additionally, large-scale simulations of the universe incorporate dark matter to see how its distribution affects the formation and evolution of galaxies, matching these simulations with observations to test theories of dark matter. While black holes themselves do not solve the mystery of the universe's missing mass, the study of black holes contributes to our understanding of the universe in other profound ways. For example, the detection of gravitational waves from black hole mergers provides new insights into the properties of black holes and tests of general relativity under extreme conditions. These discoveries, in turn, inform our understanding of cosmic structure and evolution, indirectly supporting the search for dark matter by improving our knowledge of the universe's overall mass distribution and behavior. Moving away from mass, how do black holes contribute to the universe's expansion? The role of black holes in this cosmic expansion is indirect. They do not contribute to the expansion of the universe in the way dark energy does, a mysterious force that is accelerating the expansion of the universe. Instead, black holes are a part of the universe's overall matter-energy content, which, according to general relativity, influences the universe's dynamics. The energy density of the universe, including dark energy, dark matter, and ordinary matter, of which black holes are a part, determines the rate of expansion through the Friedmann equations, which are solutions to Einstein's field equations of general relativity. One could speculate about the role of supermassive black holes found at the centers of galaxies in the context of cosmic structures and evolution. These black holes can influence the formation and development of galaxies, which are the building blocks of the large-scale structure of the universe. While they don't directly affect the expansion of spacetime, their gravitational influence contributes to the way matter is distributed and how galaxies cluster together over cosmic timescales. Furthermore, the interaction of black holes with their surroundings, including the accretion of matter and the subsequent emission of radiation and jets, can inject energy into the surrounding medium. This process can affect the formation of stars and the evolution of galaxies, indirectly influencing the large-scale structure of the universe. However, these processes occur on scales much smaller than those at which the expansion of the universe operates. The discovery of gravitational waves from merging black holes by observatories like LIGO and Virgo provides a new way to study the universe. While these observations focus on the behavior of space-time and gravity at local scales, they also contribute to our understanding of the universe's overall properties, including its expansion history. By studying the distribution and frequency of black hole mergers throughout the cosmos, astronomers can gain insights into the history of galaxy formation and evolution, which is intertwined with the expansion of the universe. Now, what is the role of black holes in cosmic recycling? When stars end their lives, especially massive ones, they can collapse under their own gravity to form black holes. This process is accompanied by the release of material through supernovae explosions, contributing to the cosmic recycling of matter. The material ejected enriches the interstellar medium with heavier elements, which can then form new stars, planets, and other objects. In this way, black holes can be seen as catalysts in the cycle of stellar evolution and death, indirectly influencing the composition and distribution of matter in the galaxy. Supermassive black holes, residing at the centers of galaxies, have a more direct role in cosmic recycling. They accrete vast amounts of gas and dust from their surroundings, which heats up and emits intense radiation before crossing the event horizon. This radiation can exert significant pressure on the surrounding gas, driving galactic winds that distribute material throughout the galaxy. These winds can both suppress star formation by blowing away gas and stimulate it by causing gas to compress in certain regions. Thus, supermassive black holes contribute to regulating the rate of star formation in galaxies, influencing their growth and evolution. Moreover, the jets of particles ejected from the regions around black holes at nearly the speed of light can inject energy into the intergalactic medium, spreading matter over vast distances. This distribution of matter and energy plays a crucial role in shaping the large-scale structure of the universe and in seeding regions for future generations of stars and galaxies. Black holes also contribute to cosmic recycling through their interactions with other black holes and stellar objects. For example, when two galaxies merge, their central supermassive black holes can eventually merge as well, releasing gravitational waves and potentially flinging stars and other material out into the cosmos. This redistribution of matter adds another layer to the complex process of cosmic recycling. As we near the end of our journey, what experiments could test the theory of living inside a black hole? Advancements in computer technology enable researchers to simulate the intricate dynamics of black holes, including the environment near and potentially inside them. These simulations, while theoretical, provide valuable insights into how information might behave in the vicinity of a black hole, approaching the speculative idea of communicating from within a black hole to the outside universe. The search for Hawking radiation, a theoretical emission predicted by Stephen Hawking, stands as a testament to the quest for understanding quantum effects at the event horizon. Detecting this radiation would mark a significant leap in bridging quantum mechanics and general relativity, offering indirect evidence supporting the complex nature of black holes and potentially shedding light on the fabric of the cosmos. Observational studies of black hole accretion disks through high-resolution imaging, such as that achieved by the Event Horizon Telescope, allow scientists to peer into the regions surrounding black holes. These observations aim to decode the behavior of matter under the sway of a black hole's gravity, offering clues to the extreme conditions that would be faced by any observer venturing close to or inside a black hole. Parallel to empirical efforts, theoretical advancements in quantum gravity strive to reconcile the microscopic world of quantum mechanics with the macroscopic realm of general relativity. This theoretical pursuit is essential for understanding the true nature of singularities and the event horizon, providing a framework that could one day enable the testing of hypotheses about the universe's structure and the enigmatic role of black holes. The groundbreaking detection of gravitational waves from the collision of two black holes by LIGO and Virgo has provided tangible evidence of their existence and offered insights into their properties. This discovery not only confirmed a major prediction of Albert Einstein's theory of general relativity, but also opened a new window into the cosmos, allowing us to observe the universe in a way never before possible. The observation of gravitational waves represents a monumental achievement in physics, and has ignited a renewed interest in astrophysics and the study of the universe at large. High-resolution imaging of the black hole in the galaxy, M87, by the Event Horizon Telescope collaboration marked another milestone, providing the first ever image of a black hole's shadow. This achievement brought black holes from the realm of theoretical physics into the visual domain, offering a new perspective on these cosmic objects and fueling public and scientific interest alike. Theoretical advances in understanding black holes, including Stephen Hawking's prediction of Hawking radiation, illustrate the ongoing dialogue between quantum mechanics and general relativity. These discussions not only deepen our understanding of black holes, but also drive forward the search for a unified theory of physics that can describe the universe at both the largest and smallest scales. The role of black holes in cosmic recycling, from their formation in the cataclysmic collapse of massive stars to their influence on the formation of galaxies, highlights the interconnectedness of all cosmic phenomena. This realization encourages a holistic view of the universe and emphasizes the importance of interdisciplinary study in uncovering the secrets of the cosmos. For aspiring scientists, black holes embody the unknown and the yet-to-be-discovered, symbolizing the very essence of scientific inquiry. The challenges in understanding black holes and their extreme environments offer endless opportunities for innovation in technology, observation techniques, and theoretical modeling. The pursuit of knowledge about black holes teaches valuable lessons in perseverance, creativity, and the importance of questioning established notions, shaping not only future scientists, but also the way we understand the universe. As we stand on the brink of cosmic discovery, gazing into the depths of black holes, we are reminded of the vastness of the universe and the minuteness of our place within it. These enigmatic entities challenge not only our understanding of physics, but also our perception of reality, time, and existence itself. What secrets do black holes hold about the birth and fate of the universe? How do they shape the cosmic landscape and the very fabric of space-time? The pursuit of knowledge about black holes is more than a quest for scientific understanding. It is a journey into the heart of existence, prompting us to question the nature of reality and our role in the universe. Do black holes, with their incomprehensible power and mystery, serve as gateways to other universes, hidden dimensions, or unknown forces that govern the cosmos? What can they teach us about the origins of space and time and the ultimate destiny of all things? Thanks for watching, and make sure to subscribe to our channel, Spacedust. See you in the next one.